The first lecture of this morning will be given by Professor Xincheng Xie from Peking University. The title is Spin Current and it's superfluid. Let's welcome Professor Xie.
Okay, can people in the back hear me? Okay. I'm very glad to be here, and as Professor Chen mentioned, today I will talk about the spin current and particularly whether the spin current can also become a superfluid, become a superconductor. Basically, we can use a simple name, simple term, whether it's possible to have a spin superconductor. Okay, that's the focus of my today's talk. And hopefully at the end of the lecture, I will be able to convince you it is possible to achieve spin superconductor. Okay. Let me acknowledge my collaborators in this work. The most important collaborator is Professor Xincheng Xie. At the time when we start working on this project, he was at the Institute of Physics. Recently, he also moved to Peking University. The other two is Zhao Jiang, who was my former postdoc, now is professor at the Beijing Institute of Technology. And then another collaborator is Professor Yu Yue at the Institute of Theoretical Physics, Chinese Academy of Sciences. Okay, here's the outline of my lecture. At the beginning, I will talk about some basic properties of a spin current. And I noticed that our workshop is partly on topological insulator, another part is on Spintronics. I think probably the concept of the spin current already appeared many times during the workshop. But anyway, I will still discuss some basic properties of spin current from my perspective. Then I move on, try to discuss whether this spin current can become a supercurrent, superfluidity. So we call it spin superfluidity or spin superconductor. And I propose a concrete possible experiment system to realize such a spin superconductor, namely the ferromagnetic graphene as a possible candidate system to achieve the spin superconductor. Okay. And after that, I will give some discussions of our result on a spin superconductor. All these discussions, I will try to make comparisons with another type of a superconductor, which you are familiar with, namely the charge superconductor. Okay. I will make a comparison, the similarity and the difference between the spin superconductor and the charge superconductor. And I will give a brief conclusion. Okay, the spin current, one of the very naive definition is basically I wrote down here. So we all know that the carriers in solid state systems, the carriers are electrons. Electron, apart from its charge, another important property of the electron is it contains a spin. And there's two components of spin. We normally call it spin up and spin down. So the charge current basically is the sum of these two components. Okay, since each component, whether it's up or down spin, carries the same amount of charge. So the charge current is the sum of these two. And the very naive definition of a spin current basically is take the difference of these two, of a spin up and a spin down. Okay. So in normal case, when you have a charge motion, spin up or spin down, move in the same direction with the same velocity, in that case, the spin current is zero. You have a charge current. But it is possible to realize situation such that spin up move one direction and spin down moves in the opposite direction. And here, in order to make the picture clear, I spatially separate where spin up and spin down. But in a real system, they are together, right? In a same, could happen in the same location. So spin up in one direction, spin down in the opposite direction. And if they move with the same velocity, such that the charge current will be zero, okay? Then you have a non-zero spin current. In this case, we say that you have a pure spin current without any charge current. But of course, there are many situations you have both spin current and charge current. For instance, in a ferromagnetic systems, if it's more favorable to have spin up electrons and more spin up electrons than spin down electrons, then in this case, you have, if you have a current in the normal situation, it contains both charge current and spin current. So what for this talk, we are mainly concentrated on the case that you do not have a charge current, but you have a pure spin current. And the question we ask ourselves, whether this spin current can also become a supercurrent. So, so this is the sort of mathematical simple definition of a spin current. But whether in physics we also always ask the question whether it's if you have a quantity defined, we have to ask whether it's a physical quantity. Basically, we have to make sure that whether it's a measurable physical quantity. In a lab, you can detect with a spin current. Okay. Now these days, there are several ways to detect spin current. Here I mentioned one of the methods to detect spin current is through so-called spin Hall effect. Okay. So here I draw a simple picture of a simple spin Hall system, and I'm sure the spin Hall, this concept of spin Hall probably already appeared in this workshop in this summer school. So again, in order to talk about spin Hall, we can also make a comparison with the Hall effect we're familiar with, namely the charge Hall effect. The charge Hall effect is that if you have a sample, for simplicity, let's consider two-dimensional samples. And the charge Hall effect is in the presence of a strong in the presence of magnetic field. So if we have two-dimensional samples, if we apply magnetic field perpendicular to the 2D surface, if you apply also a voltage or electric field along the longitudinal direction, that's called the x direction, along this direction, x direction. And then the electron moving along the x direction, it has velocity. If you apply magnetic field perpendicular to this direction, the velocity, the charged particle the magnetic field will have a Lorentz force on the charged particle. So the Lorentz force is a V cross magnetic field. So if magnetic field in this z direction and velocity in the x direction, in this vertical direction, along the y direction, you will have a Lorentz force. So in the presence of Lorentz force, the positive charge will move in one direction, and the negative charge move in the opposite direction. So you will have a charge tying up in your sample. On the one edge of your sample, you have more positive charge. On the opposite edge, you have negative charge. That will give you another electric field along the y direction to balance the Lorentz force. So when you reach the equilibrium, there will be more positive charge on one end, negative charge on the other end. So there will be electric field on this direction. We'll have a so-called Hall voltage. You can measure the Hall voltage. Okay. So that Hall voltage divided by this current will give you the Hall resistance. So you will see the charge Hall effect give you the charge Hall effect. In the classical case, the Hall resistance we know, since it's proportional to Lorentz force, it's linear in magnetic field. Okay, it will be linear in magnetic field. But in a strong magnetic field situation, you achieve so-called quantized Hall effect. So there will be a quantized plateau. Later on, I will also mention a little bit. I noticed that the last day of the summer school, Professor Xincheng Xie from Tsinghua University, he will talk about the quantum anonymous Hall, and I'm sure he will discuss more in detail about the quantized Hall effect. Okay, so this is typical the charge Hall effect. But today we want to discuss spin Hall effect. So in the charge Hall effect, due to the Lorentz force, you have charge. Although you originally you apply the electric field along the x direction, you have current flowing in the x direction. Due to the Lorentz force, you also have the Hall voltage in the direction perpendicular to where you apply electric field. Okay, you have Hall voltage. The spin Hall effect. So the reason you achieve this Hall effect is because you have a charge current flowing in this direction. You have more positive charge on one end and negative on the other. So you have a charge moving, charge current also in the y direction. Okay. The spin Hall effect is somewhat different. First, the condition for the sample is different. You do not to apply a magnetic field perpendicular to the sample. What you need to have is that the samples contains a strong spin orbital interaction. Okay. Due to this spin orbital interaction, what happens is that the spin up electrons tends to move to one direction, and the spin down electrons move in the opposite direction. So at the end, you have a spin up electrons piling up at one edge of the sample, spin down on the opposite edge. So instead of a charge piling up, you have a magnetic moment, magnetic dipole piling up at one edge and the opposite edge has different dipole moments. So that dipole moments can be detected experimentally. Okay, one is the sort of the red curve, the other is the blue curve. So you have two edges, you have two opposite dipole moments. That tells us there's a spin current because spin up moving one direction, spin down in opposite direction. It fits our naive definition for spin current. So in this case, it's the spin current moving in the vertical direction instead of charge current. So that's an indirect way to measure, one way to measure the spin current. So that's one way of measuring spin current. So, but you probably noticed that I always use the word naive definition of spin current. Actually, if you want to analyze the spin transport in more detail, it's a little bit more complicated. So we want to go through some of the more basic concept of spin transport. Again, we want to make comparisons with charge transport. We want to achieve our goals. So the charge transport, there's a very basic equation. It's a so-called charge continuity equation. Okay, so the basic it's from the basic result that charge is always conserved. Okay, so in terms of equation, is what it tells us if you have a local charge density, its time derivative plus the divergence of the charge current density equals 0. Okay, so this tells us charge is conserved. Basically, you can take any region if you draw a surface of this region, and if you the first term, if you integrate out, is to the volume integral of this region. The first term tells you what is the charge change within this volume, and what is the charge change is always equals what's the charge leaves out from this surface. So it tells us total charge is always conserved. So the integral version of this differential equation will clearly show that charge is always conserved. Okay. So this continuity equation basically tells us the charge is conserved. Of course, you can write this is true in classically or quantum mechanically. So quantum mechanically, you can define what is the charge density. Basically, it's a wave function square multiplied by a charge E. Here, just use the unit as a charge E. So I'll write this E here. And then the current density is E times velocity. So it's just velocity between the two wave functions, phi plus and phi. Take the real part of this. So this is the current density. So I'm sure you have learned this in your quantum mechanics class, and you can show that it satisfies continuity equation. Now, so since we are talking about the spin transport, we want also try to extend whether it's possible write this equation for spin transport. So first you have to define what is the spin density. Okay, is that a charge density? And it turns out you can easily define the spin density. Of course, spin it's a vector. So quantum mechanically, if you want to write down the local spin density, it's the spin operator, which is a vector in between of these two wave functions. Okay, phi plus and phi. So you can write down the local spin density. Now you can just do what we have done for the charge transport. Look at its time derivative, right? Time derivative of this local density. Then the time derivative of this, from the Hamilton equation you have learned, any operator's time derivative equals commutative of this operator with the Hamiltonian. Any operator's time derivative equals the commutative of this operator and this Hamiltonian. Okay. And then depends on what Hamiltonian you choose. You just need to carry out the spin operator, basically polymetrics, the commutator with Hamiltonian. So if your simple system, if the Hamiltonian does not depend on spin, of course, then this time derivative is 0. Okay, so it's time independent. But of course, if we want to talk about the spin transport, the Hamiltonian has to contain some spin. So let me write down some general form of the Hamiltonian. And this is just the discussing is very general, but in order to carry out the mathematics, we write down some specific concrete Hamiltonian. So here, the Hamiltonian, you can see, let's assume that normally it has the kinetic energy term and the scalar potential term. Okay, that's what's up here. And if you have a Magritte field, the spin will couple to Magritte field through at least the Zeeman term. Okay. Then you, as I mentioned, that in our case, we want to talk about the spin transport, and like the spin Hall system, it has a spin orbital interaction. So we will write down a so-called Rushbach spin orbital interaction, and you can see the spin couples to the momentum, to the orbital motion. So this is one form of the spin orbital interactions. So once you have this Hamiltonian, of course there are two terms which does not commute with sigma, with spin. So it has non-zero commutative. Okay. So due to the external magnetic field, and also due to the spin orbital interactions. Since it already has sigma in it, it won't commute with sigma. Normally, it won't commute with sigma. Then you can carry out this time derivative of this spin operator. So those are the simple calculations. You just need to calculate it basically sigma commutated with another sigma. Okay. Polymetrics, commutator relations of polymetrics. So at the end, what's the result? The result is that the time derivative was local spin density operate. You will have two terms. Okay, you will have two terms. The first term, okay, the first term is right down here. And if you analyze what's in this first term, it has this spin operator here. Also in front of this has another operator. Let's first ignore the spin orbital interaction. Let's take the alpha equals 0. Forget about the spin orbital interaction term. So this just gives us v p divided by mass. It's just velocity v times the s. V times the s. Okay. But both of these are vector. So v times the s basically give us a tensor. Okay. Give us a tensor, second rank tensor. So it's just velocity times the vector. So this is what normally we call the spin current. The more regular definition or more standard definition for spin current, it is a vector, or it is a tensor. Okay, it's a v times s. So if you compare with the charge current density, it also has a v. Then the charge E changes to s spin. So it becomes the spin current density. Okay? I didn't write the E here, I just take the E as 1. But if you change the E to the S, it becomes the spin current density. But the difference, charge current density is a vector. Spin current density it is a tensor. And also, if you have spin orbital interaction, it will also contribute another term in the velocity operator. So that will be contribution. Basically, this you can consider that the spin orbital interaction give you another give you a equivalent of sort of magnetic field in the momentum representations. Give you another term because you have sigma cross something. Anyway, so this is the spin current density people talked about it before. Okay. And our early work, we made a contribution. We noticed that this is not enough. Okay, so you just so spin transport that two contributions. One, what we call is linear due to the linear momentum. So you can call it linear spin current. Linear spin current, because what appears is the linear velocity appear in this definition of spin current, the first time. But you also notice that there's the rotational motion. Since the spin is a vector, you can also make a rotational motion. This vector can rotate. It has rotational motion. And the first term from the rotational motion is quite familiar to you, right? It's the B cross the S cross the magnetic dipole, cross the spin. So if I have a spin in the presence of magnetic field, it will rotate around the magnetic field. So that's represented by the first term. Okay? So the spin motion, apart from a linear motion, will have a rotational motion. Also, spin orbital interaction give you effective magnetic field in the momentum space, right? So it give you a magnetic field, effective magnetic field, depends on the momentum, and the spin will rotate around that effective magnetic field due to the spin orbital interaction. Okay. So if we talk about the spin transport, you have to remember not always two pieces. One is represented by a linear motion, the other is by angular motion. Okay. So this angular motion is what we call the angular spin current, or for the rotational motion. And if you look at the quote continuity equation, if you do not have this rotational motion, angular motion, then it is conserved, right? If you do not have this term, it's just the same as this, except you have three components, because you have three components. So each component is conserved, if you do not have angular rotational motion. However, due to the rotational motion, which appears either through an external magnetic field or due to the spin orbital interaction, then in the spin transport process, its spin is no longer conserved quantity, right? Because you have a non-zero term here. If you have a zero term here, which is the same as the charge motion, except you have three components. But due to this term, it's no longer conserved. So the spin transport in the presence of external magnetic field with a strong spin orbital interaction is not conserved. Okay. It's not conserved. So this is the similarity and difference if you compare with the charge transport. Okay, so here is what you were able to write down. So the linear spin current, which is people are relatively familiar with, it's just velocity times s, okay? Linear velocity times s. The rotational spin current, you can simply write down as omega cross s. Omega is the angular velocity, right? So the case you are familiar with, if you just add a magnetic field, you have a rotational motion, so you have angular velocity proportional to the magnetic field, just omega. And the spin orbital interaction also give you another omega. So you can write down as omega cross s. So you have these two terms here. And if we want to come back to the naive definition of the spin current, at the beginning I said the naive definition of spin current is spin up moving in one direction, spin down moving in opposite direction. That's the case if you already fixed the s just along the z direction, so you only have up and down. Okay. In that case, this linear spin current go back to this naive definition of spin current. So up to now, I analyze what's the spin transport, what's spin motion. Okay, I try to make a comparison with the charge transport. There's some similarity and a difference. And I also use one type of experiment